Welcome to this explainer. We're jumping right into a massive dilemma today, one that literally every single operating system has to deal with. From that smartphone sitting in your pocket all the way up to the massive servers running the internet. Think about it for a second. How exactly does a CPU know when a piece of hardware needs its attention? Like when you tap a key or a network packet suddenly arrives, how does it know without wasting all of its precious processing time constantly checking? Well, that brings us to the ultimate system design matchup: polling versus interrupt handling.
Here is the game plan for today. We'll start with 1. Meet the event handlers. Then 2. Strengths and weaknesses. 3. The evaluation criteria. 4. Real-world scenarios. And finally, 5. The final exam verdict.
All right, part 1. Meet the event handlers.
To really get this, it's basically like a road trip. Polling is cyclical. It's the equivalent of a kid in the backseat repeatedly asking, "Are we there yet? Are we there yet?" The CPU is actively checking the device. On the flip side, interrupt handling is like setting a GPS alarm so you can just sleep in the passenger seat until you actually arrive. In this case, the device reaches out to the CPU, not the other way around.
Let's formally introduce our first contender. Polling is when the CPU repeatedly checks a device or a specific condition to see whether anything needs attention. So the really crucial takeaway here is that polling is highly proactive. The program itself is entirely in the driver's seat, choosing exactly when and how often these checks are going to happen. And in the other corner, we have interrupt handling. This is when a device or an event sends a specific signal to the CPU the exact moment attention is required. In stark contrast to polling, interrupts are purely reactive. They literally force the CPU to completely pause its current task, go service the interrupt, and then carefully return to its previous work once that job is done.
Let's move on to part 2, strengths and weaknesses.
So how does polling actually work under the hood? It follows a very predictable, super simple step-by-step loop. The program enters the loop, it checks a status register or an input flag, and if nothing has happened, it just shrugs and says, "Okay, I'll check again later." If an event is ready, the CPU processes it. It's straightforward, it's really simple to implement, and it gives the programmer total control over the timing.
Interrupts, though, that's a significantly more complex sequence. Out of nowhere, a device raises an interrupt request. Suddenly, the CPU has to scramble to save its current state so it doesn't lose its place. Then, an interrupt service routine jumps in to handle the event. And finally, the CPU has to restore its state and resume its earlier task. As you can see, it's a whole lot of juggling.
When we put them in a direct head-to-head comparison, polling's massive advantage is that sheer simplicity and tightly controlled timing. But interrupts, they are the absolute champions of efficiency. Because the CPU isn't wasting time constantly checking, it can actually get other work done. This results in incredibly fast responses to completely unpredictable events.
But hey, every superhero has a weakness, right? Polling can drastically waste CPU cycles and drain battery power if it's constantly checking a device that rarely does anything. Conversely, interrupt handling is notoriously difficult to debug. Too many interrupts can create massive system overhead, and if they aren't strictly controlled, you can even open the door to security vulnerabilities and totally unexpected execution paths. Which brings us to part 3, the evaluation criteria. Whenever you're evaluating these methods, you really want to look for specific patterns. Notice how polling perfectly suits very frequent and predictable events, especially on systems plugged into mains power where wasting a little CPU isn't a huge deal. On the other hand, interrupts are the undisputed winners for irregular, unpredictable events, especially on battery-powered devices where saving every drop of energy is absolutely critical.
Let's put this to the test. Part 4. Real-world scenarios.
Okay, here's our first scenario. Imagine you have a smartwatch, and its sensor needs to check your heart rate exactly once every single second. Based on everything we've just covered, would you use polling or interrupts to design this? Really think about the event frequency and the predictability here.
If you guessed polling, you are spot on, because that interval is fixed, known, and highly predictable, literally exactly 1 second. A simple polling loop is actually the best fit. It's a simple embedded system where tight, controlled timing is exactly what the designer is going for.
All right, let's try another one. You're working on a laptop. You are busy typing up a document, and totally random Wi-Fi packets are arriving from the network. Which method should handle those incoming network packets? Polling or interrupts?
Interrupts win this round, hands down. Network communication is highly unpredictable. If your laptop CPU had to constantly pause your typing just to pull the Wi-Fi card to see if a packet arrived, it would completely waste processing power. Interrupts let the CPU focus entirely on your typing until a packet actually shows up.
Let's raise the stakes for this last one. You're designing a system for a heavy machinery factory. There is an emergency stop button that, if pressed, must halt everything immediately to prevent a total disaster, polling or interrupts.
This absolutely 100% must be an interrupt. An emergency stop is the very definition of a real-time warning. It requires a drop-everything, immediate responsiveness that a polling loop, which might actually be busy checking something else at that exact millisecond, simply cannot guarantee.
All right, let's bring it all home. Part 5, the final exam verdict.
A really strong evaluation, whether for an exam or real-world engineering, recognizes that system design isn't just about one method being objectively better than the other in a vacuum. It's always a balance. It's this constant push and pull between the efficiency of interrupts and the tight control of polling. And honestly, that leads right into the most common mistakes people make. Please avoid the massive trap of assuming interrupts are always superior just because they sound a bit fancier. In simple systems, polling is brilliant. Also, don't confuse fast with efficient. Sure, polling can check a device incredibly fast, but if the device is empty 99% of the time, that speed is just a massive waste of processing power.
If you want to construct that perfect, top-tier model response, anchor it with this core summary. Always start by defining both methods. Then, compare their overhead and responsiveness. Apply them clearly to the scenario you've been given, and finally, deliver a reasoned judgment that references specific system requirements like the power source or predictability.
As we wrap up this explainer, I want to leave you with one final thought to chew on. Take a second and literally look at the device you are using to view this right now. Your keyboard, your mouse, your Wi-Fi card, your internal clock. Ask yourself, which heavyweight contender is managing the data at your fingertips right at this very second? Is it proactively polling, or is it silently waiting to interrupt? Keep that question in mind, and I promise you'll start seeing operating systems in a whole new light.